So today what I have planned is to kind of continue on with heat transfer stuff. And so we're going to do that now. Okay, so last time we just kind of went over stuff that hopefully should be fairly old hat from thermo. So just some terminology, and we started talking about a little overview of conduction. And then once we get past this kind of like review of heat transfer in general, we're going to talk about conduction in a lot more detail today. Okay, so when we were talking about the mechanisms of heat transfer, we said there's three. The first one we outlined here was conduction. The next one is, did I say conduction or convection? The first one we did was conduction. Now we're going to talk about convection, which is heat transfer between a solid surface and an adjacent moving fluid at another temperature. So this is between a solid surface and an adjacent moving fluid at another temperature. This involves a moving fluid. And it essentially bundles up the heat transfer that rises from the fluid moving, as well as the heat transfer that happens because heat just flows through a material. So this involves diffusion, which is just another way of saying conduction, and advection. All right, so convection is diffusion and advection, both of them together. Conduction is just diffusion. Okay, so you can have conduction through a fluid if it's at rest. If the fluid's moving, then you have both conduction and advection. Does that make sense? Okay, so just to kind of reiterate that, there's two key players in convection. So diffusion, that's heat being transferred from one area to another just because there's a temperature gradient and there's material there. And then there's also advection. So this is essentially heat being carried along by the flow. So since the flow is moving, since the material is moving, the heat goes along with the material. All right. So an example of kind of the type of problem that we'll look at when we're talking about convection is, for example, having a warm plate at some temperature Ts. So that's the surface temperature. And then we also have a fluid in contact with this plate that's moving in some way. This is our fluid. All right. Convection can be categorized into two different types. The first one is forced convection. So this is when the fluid motion is driven by an external source. So the fluid motion driven by an external force. So things like a fan or the wind, for example, that would be a forced convection scenario. And then there's also natural convection, which is actually really, really cool. I find this very interesting. And this is fluid motion is actually being driven by the differences in density caused by there being a temperature gradient. So when a gas is hotter, it's less dense. And so that will cause mixing naturally, hence natural convection. So here we have that fluid motion is driven by buoyant forces. And those forces are developed due to density differences. And those density differences are due to temperature variations. All right, so kind of the idea behind this is heat rises, right? So if you have, for example, if you have a hot plate kind of at the bottom and then a cooler plate at the top and you have a gas in between it, this is the type of mixing that you observe. So the fluid or the gas at the bottom plate is getting heated by that bottom plate. As that happens, it becomes less dense and it starts to rise relative to the cold air at the top that starts to sink because it becomes more dense. Okay. And this is actually called, this is Rayleigh-Benard mixing. Convection or mixing. Oh, and this accent should be on the E, not the N. There. Okay. Convection is governed by Newton's law of cooling, which hopefully you've seen in 2500 already, right? Maybe? Yeah? Okay, cool. So here we have the heat flux due to convection. So this is heat flux due to convection is equal to this coefficient H times the difference in the surface temperature and then of our surface and then the background temperature of our fluid. So I'm going to talk about each of these separately. So this temperature difference here, this is temperature difference between temperature of the surface. So that's TS. And the background temperature of the fluid. All right. Which is T infinity. This guy. Okay. We also have this coefficient H. So H is the convective heat transfer coefficient. And it has units of watts per meter squared Kelvin. All right, so that means that our temperature difference, we have to use Kelvin for these, for the units to work out, okay? H is a empirical value. Which is based on fluid properties. So things like the flow pattern, and things like that. It is not a material property at all. All right, so if you remember, kind of, this is similar to what our heat flux due to conduction equation looked like. It kind of looks like Fourier's law of conduction. where K, the coefficient K in front of that equation was a material property. This one is not. And so this value is actually empirically fit to Newton's law of cooling. All right, so what that means is lots of experiments were done, Q dot was measured, and the temperature difference were measured, and then all of those data points were used to find H. Okay. Okay, so to talk about kind of how H is not a material property a little bit more, this value is going to depend on fluid velocity properties, geometry of the surface, and all that good stuff. And just to keep the notation completely clear, sometimes natural convection is called free convection, but I'm going to use natural throughout. So natural convection. So here you can see that we have for natural and forced convection, it's divided into gases and liquids here. But there's a pretty big range of what H could be, especially for liquids. So ranging from 50 to 1,000 or 100 to 40,000. So we're going to talk about in just a minute kind of how we can be a little more specific about what H should be. But first, let's do a quick little example. So we're going to consider heat transfer out at the outside wall of a building. So consider heat transfer outside the wall of a building. All right, so we have our wall, and this is kind of a top-down view. Then we have our wind going past here. So this is wind. We're given that the surface temperature is 20 degrees C. And then far away, T delta is equal to 0 degrees C. All right. And then we're also going to assume that our heat transfer coefficient is 20 watts per meter squared Kelvin. All right, so we're just going to pick the highest value for a gas. Actually, that doesn't make sense. So wind is forced convection, right? So let's pick 25. Okay. And we want to find the heat transfer flux. So we want to find Q dot. And we're going to call the wall 0.1. And the faraway air is going to be 0.2. So our governing equation is Newton's law of cooling. So we have Q dot is equal to H Ts minus T infinity. All right, so H we already know is 25, and this is watts per meter squared Kelvin. The difference between temperature, if you use Celsius or Kelvin, will be the same. If you use Fahrenheit, it won't. So just make sure that when you're doing a temperature difference, you're using either Celsius or Kelvin, and then the units will be fine. So we will do 20 minus 0. And we end up with 500 watts per meter squared. All right, so this is the rate at which heat is being lost from the building to the external air. Okay. Okay, so that's kind of the base mechanics of how we're gonna look at heat transfer due to convection. But I want to talk about H a little bit more because this table gave us really wide ranges of H, but we can be a little more specific with it. And we're going to talk about this more in the convection unit. So this will probably be a week from today that we'll talk about it. It's common to express H as a ratio with the conductivity K. And so this is the Nussel number. It's a non-dimensional number that essentially gives us a ratio of a fluid's convective heat transfer to its conductive heat transfer capacity. And so generally what we'll do, and we'll talk about this more in the convection unit, but generally H is specified using the Nussel, by knowing the Nussel number. So when we do convection, essentially that entire unit is going to be about figuring out what the Nussel number is and then finding H, and then we can find Q dot. Okay. The third type of heat transfer that we can encounter is radiation. And so energy emitted by all matter via photons is due to changes in electron configurations, and it is transported by waves. There's no medium required for this type of heat transfer. Which means that you can have a vacuum and still have this heat transfer taking place. So this is how, heat transfer from the sun gets to us, for example. Okay. Did you guys talk about radiation in 2500 at all? No? Okay. This is the extent to which I'm going to go through it in this class. So it'll be kind of just a very light overview. But the maximum rate at which thermal energy can be radiated by a surface at some temperature, T is defined by the Stefan-Boltzmann law. So that's what this is right here. So we have Q dot for radiation is equal to epsilon times sigma T to the fourth. And actually, sorry. So without the epsilon, this is a theoretical limit. So this is black body radiation or ideal radiation. But in reality, it's less efficient than this typically. So it's going to be a lesser number than that. So that's why epsilon is introduced into here. So this epsilon value is the emissivity. And you can kind of think of this as a radiation efficiency. Okay. This depends on the type of material that you have, and it's always going to vary from 0 to 1. Okay, just like efficiency would. So if you have reflective materials, so at the top of this table, you see polished silver, polished copper, polished gold, foil. Generally, visually reflective things are going to have a lower emissivity. And then things that are more opaque or dark. So if you have wood, vegetation, paper, water, black paint, all that stuff has a much higher emissivity value. Okay. So these are just typical values of emissivity. All right, so I kind of already said this verbally, but these items have a tendency to reflect. And then these have a tendency to absorb. All right, so epsilon is going to always be between 0 and 1. Epsilon equals 1 is essentially the sun. And then materials with high emissivity have a tendency to absorb radiation. Okay. Okay. Radiation that's received on a surface can either be absorbed by the material, absorbed by the material. It can be reflected away, or it can be transmitted through the material. Okay, so the material properties, there's 3 material properties that essentially describe how a material is going to behave in each of these 3 ways for how it can deal with incident radiation. Oh, I guess I should say, so radiations that is received, this is sometimes called incident radiation. All right, and so I've color coded these. So absorptance, alpha is the tendency to be absorbed, radiation would be absorbed by the material. Reflectance is its tendency to be reflected. And then transmittance is obviously to be transmitted. All right, so those are all linked together. And essentially what we can do is we can say that whatever the Q dot value is of radiation, it's going to be divided into these 3 categories. So if we have incoming radiation, Q dot radiation, what we have is either absorption. So this is going to be alpha times Q dot radiation. It could be reflected, which is rho times Q dot rad, or it could be transmitted. And this is tau times Q dot rad. All right, and so it turns out that this is entirely, like all of the radiation will be split between these 3 ways and it goes nowhere else. So Q dot radiation is going to be the amount that is transferred through absorptance, so alpha Q dot rad, plus the amount that's reflected, rho times Q dot rad, plus the amount that's transmitted. So tau times Q dot rad. Does that make sense? All right. Kirchhoff's law of radiation states that emissivity and absorptivity of a surface at a given temperature and wavelength are equal. Which means alpha equals epsilon. And then at any given time, all surfaces are emitting energy and receiving energy. A surface will either warm up or cool down based on the balance of those 2 fluxes. So the amount that it's emitting versus the amount that it's receiving If it's receiving more radiation energy, then it's going to heat up. If it's emitting more, then it'll cool down. Okay. And so this is the governing equation for Q dot radiation. We have Q dot rad, so this is following the same convention of what we've had before. So this is our heat flux due to radiation. We have our emissivity, which we've already talked about. We also have sigma in here. And then we have this temperature difference that looks kind of similar to what we had before, but you'll notice that now it's raised to the 4th power rather than just being a temperature minus a temperature. So we have our surface temperature to the 4th power. And then we have our surrounding temperature. So this is our temp of the surroundings. Surroundings. All right, and this arises from the Stefan Boltzmann law. It would be awfully convenient if we could write the radiation equation in a form that's similar to what we've seen for conduction and convection, where we just have a Ts minus T surf. And so we want to end up with an equation that looks like this. So we'd like to have an equation of this form. But the trouble is, what is this HR then? All right, so in order to find it, what we're going to do is we are going to essentially compare this equation, so our Q dot rad equation, to the equation that we want to get to. And then I'll show you how HR is equal to all of that. So that is all of this. And here's how we got there. So we have that Q dot radiation is equal to epsilon times sigma Ts to the 4th minus T surroundings to the 4th. All right, and then I am going to break this apart into two products. So I have Ts squared minus T surroundings squared times Ts squared plus T surroundings squared. All right, so I've just expanded out that T to the 4th minus T to the 4th expression. And then I'm going to do that again for this yellow one. I'm going to highlight this one. I'm going to expand this out once more. So I have epsilon sigma times Ts minus T sur times Ts plus T sur. And then I'm going to keep around my Ts squared plus T sur squared. All right. And so you'll notice that now we have this Ts minus T surf term. That's right here. And all of the rest of this is HR. So this and this all group together to form HR. Okay. Real quickly, I'm going to show you the circuit analogy for this. So we have TS connected with a resistor to T surroundings. And there's a typo in here. There should be no F on these ones. It's surroundings, not surface. Sorry about that. I was in a convection state of mind when I wrote that, I guess. All right, and then in our circuit analogy, our resistor has a resistance R. R is equal to 1 over this HR term. And then also note that HR is going to be a function of both TS and T sur. Okay. Okay. So just to make the electric, thermal, and fluid system analogies kind of all cohesive in one table, I think I mentioned this before. If you like one of these analogies for analysis, you're welcome to use it. I don't particularly love the electric system analysis myself. It's just not how my brain works. But I just wanted to put this in here so that you can see them. So in an electric system, our voltage is going to be our effort. So we have voltage here. In a fluid system, this is pressure. In a thermal system, it's temperature. Which is T and has units of K. And then this is pressure P. Okay. Flow in an electric system is, of course, current, I. And in a fluid system, this is, of course, velocity, which we call V. And in a thermal system, this is heat flow, or Q dot. This has units of watts. Resistance in an electric system is resistance. So this has a variable R, units are ohms. Resistance in a fluid flow is viscosity. So this is mu. And then for a thermal system, we call this thermal resistance. R. And then in both electric systems and thermal systems, we have this concept of storage, energy storage. We don't really have that in a fluid system though. So that's why I have that little slash through here. So in an electric system, this would be capacitance. C. And then in a thermal system, this is thermal capacitance. Also C. All right, so we can use basic laws of circuits to equivalent thermal systems or networks. So for example, if you have materials in series, resistance gets added using a specific rule. So if we have a material at T1 to T2 to T3 to T4, and then we have a Q dot going from each of these like this. So we have Q dot 1, 2, 3. If I were to draw this as an equivalent circuit, I would have something like this. So at each of these nodes, we have our temperatures. T1, 2, 3, and 4. And then we have resistance. So at R1, we have L1 over K1. R2 is L2 over K2. And then R3 is L3 over K3. All right, so if we wanted to make this into an equivalent circuit with just one resistor and T1 and T4 at either sides of it, what we do is the following. So this is our Q dot equiv. And this is our resistance that's equivalent. So REQ is L1 over K1 plus L2 over K2 plus L3 over K3. So in series, we just add the resistances together. All right, we're gonna do something a little bit different for conductance in parallel. So what we are going to do is the following. So if we have like a composite material that looks like this. All right, so we've got Q dot going through the system like this, and it's being broken into Q dot 1, Q dot 2, and Q dot 3. The resistor or electric system equivalent of how we would draw this is the following. So our resistors are now in parallel. So this is Q dot equivalent. This is R1, R2, R3. All right, and so sorry, this is just Q dot. And we have T1 on this side and T2 over here. All right, so our equivalent circuit looks like the following. So we're again gonna do our two nodes with one resistor in between. So we have T1 and T2 here, and this is our equivalent resistance. All right, so we just, 1 over the equivalent resistance is equal to the sum of all the reciprocal resistances, just like in circuit analysis. One over R3. And then at steady state, we have that Q dot 1 plus Q dot 2 plus Q dot 3 is equal to Q dot equivalent. Okay. All right. Heat flow from a capacitive element is proportional to the rate of change of the temperature. So we have that K1 over L1 times T1 minus T2 is equal to K2 over L2 times T2 minus T3, which is equal to K3 over L3, T3 minus T4, which is also equal to T1 minus T4 divided by L1 over K1 plus L2 over K2 plus L3 over K3. All right. Thermal capacitance of a material can be calculated as a function of its specific heat capacity as well as its mass. So if we have the ability to store thermal energy, it's going to look like this. So in a thermal system, we have our little block of material here. We have Q dot in, Q dot out, and there's some T naught temperature that it has. Q storage is going to be denoted with this kind of circle with an arrow, this little, and then this is our Q storage. All right, the way that we would look at this in terms of an equivalent circuit is like the following. So we would say, okay, we have some Q dot in flowing into this node, which is T0. And then we have Q dot flowing out. And then we also have Q dot storage, and that's going to a capacitor, which is connected to ground. All right, and so our capacitor is C over A. All right, we can write down an expression for Q dot storage. So this is defined as the following. So Q dot storage is just C over A times D T naught dt. So this is the time rate of change of the temperature of that material. And C is Cp times M. So Cp is our specific heat capacity. This has units of joules per Kelvin kilogram. And then this is mass, which obviously has units of kilograms. All right, and so our capital C is capacitance, which has units joule per Kelvin. Okay. Okay, so I have a couple of examples just to get our wheels turning again with heat transfer type problems. Unless you guys want to break. You okay, or do you want to break? If you're okay for now, I'm going to do 2 examples and then we'll take a break. Okay. All right. Okay, so what we're going to use to solve these problems is essentially conservation of energy. So we're going to use the first law of thermodynamics, which is just another way of phrasing conservation of energy to solve these problems. The approach is generally going to consist of applying an energy balance to some surface or point that we're going to assume has 0 mass. And then because it has 0 mass, it has 0 capacity to store any energy. So if you remember here, Q dot storage, the capacitance depends on the amount of mass. So if we say mass is 0, Q dot storage is 0. Okay. And so if there's no storage, then we say energy in has to be equal to energy out. All right. So for example, we're going to consider the energy balance at this surface below. We want to find Q dot convection and Q dot radiation. and describe the balance at the outside surface and determine the temperature at the inner surface. All right, so we have this material, which is represented by this gray rectangle. It has a width L, and on the left-hand side, this is our inner surface. It has a temperature T in, and then on the right-hand side, we have an outer surface, T out. All right, so let's draw in kind of the heat transfer that's going on here. So we have ambient air on the outside surface. We're given a convective heat transfer coefficient and also the T infinity value. And so this implies that we have some flow going on here. And we're going to also have, because of this, convection. Okay. We also will have radiation with our surroundings. So I'm going to assume that I have my surroundings temperature the same as our ambient air. So this is 297. Okay. All right, this is for radiation. All right, so we also are going to have a Q dot radiation. All right, I'm drawing my Q dots in the positive sense. So they're going out from the surface to the surroundings. If this choice was wrong, we will end up with a negative sign, just like how we did in the fluids unit, okay? And then we also have conduction going on here inside of the material. And let me correct this. This should be a lowercase k. All right, so we're given all of our material properties for that little chunk of material that we have. So we know what L is, we know what the value of K, epsilon, and then we also are given the T outer surface and sigma. All right, so we have everything at our disposal here to look at conduction, convection, and radiation for this material. Okay. Okay, so let's look at each one. I'm going to start with conduction. All right, so we have that Q dot conduction is equal to K over L, T in minus T out. All right, this is just Fourier's law of conduction. We are given K already, so this is 0.7 watts per meter K divided by L, which is 0.003 meters, times, we want to find T in, so I'm going to leave it there, minus T out, which is 307 Kelvin. All right, so we want to find this. So it stays as a variable for now. Next, we want to have a look at convection. All right, so we know that Q dot convection is H times T out minus T infinity. I'm using T out here instead of TS because our surface is T out. Okay, so this is Newton's law of cooling. We're given all of this information already, so we can just plug it in. So H is 2 watts per meter squared Kelvin. T out is 307 Kelvin minus T infinity is 297 Kelvin. And I want to just pause right here. So if we drew our Q dot pointing away from the surface, that's our positive orientation for Q dot. If it turned out that the ambient air is heating our surface, we would have T infinity would be greater than T out, and so we'd pick up a minus sign, which means that heat is flowing from the air to the surface. Okay. All right, and so when we do that math, or arithmetic, I guess, we get 20 watts per meter squared. And then last but not least, let's do radiation. So Q dot for radiation is equal to epsilon times sigma T out. So we have our surface temperature to the fourth power minus the temperature of our surroundings to the fourth power. All right, and we have all of this information as well. So epsilon is 0.95. Sigma is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the fourth. I need a little bit more space here. Times 307 to the fourth minus 297 to the fourth. All right, so when we do that arithmetic, we get 59.4 watts per meter squared. Okie dokie. So we have all of our Q dots accounted for here, and we have highlighted that we need to find T in. We don't have that yet, but we need to connect the Q dots together in order to figure out what T in would be. So we're going to do our energy balance at the T out surface. So we're going to do our energy balance here. Okay. So I'm going to just draw my surface as a straight line. We're going to assume it has no mass. All right. And so we have Q dot conduction coming into it. We have Q dot convection leaving and Q dot radiation leaving. Again, I'm just radiation leaving. And then I am going to draw it in here just so that you know it could exist. But if we had Q dot storage, it would look like this. All right, so I've drawn this in exactly the same way as what I drew on kind of the more physical representation of the system. And all of the Q dots are oriented positively still. All right, our conservation of energy equation looks like this. So we have the change in energy with respect to time over a control volume is equal to E dot in minus E dot out. All right, this term on the left-hand side is Q dot storage. And the right-hand side is essentially the in versus out from the picture that I've just drawn here. So we have the only thing coming in is Q dot conduction and then minus Q dot convection plus Q dot radiation because those things are leaving. All right. Again, if you were to have drawn your arrows incorrectly, because of the minus sign for minus E dot out, if like say, for example, Q dot convection actually was flowing in, you'd end up with a negative Q dot convection here and it would all work out sign wise. So as long as you're consistent with your picture and everything, then you should be good. Any questions so far? Does this feel okay? All right, and then we are assuming, we're going to assume steady state. So that means that Q dot storage is 0. So if you recall, when we assume steady, that means the time derivatives are zero. So d dt equals zero, thus q dot storage equals zero. Okay. So this means that our equation then just becomes q dot conduction is equal to q dot convection plus q dot radiation. All right, what comes in is going out. Okay, so I am just going to plug in our results that we already found. So we have that 0.7 divided by 0.003 times Tn minus 307 Kelvin is equal to 20 watts per meter squared. This is our conduction, or I'm sorry, our convection value plus 59.4 watts per meter squared. This is our value from radiation. All right, and then we're just going to solve this thing for Tn, and we get 307.8 Kelvin. In case anybody is interested to see what the equivalent circuit looks like for this, I will draw it for you. But I'm not going to do the analysis. So our equivalent circuit is going to look like the following. So we have Tn connected with a resistor to T out. So this is our Q dot conduction. We have Q dot storage. Denoted with a capacitor here, and then we have T infinity and T surroundings. And this is our Q dot convection and our Q dot radiation. If anybody is feeling stressed about the equivalent circuit analysis, I will not make you do it. I'm just showing it to you. Hopefully that did not feel too bad. Any questions on that problem? No? Okay, so just to recap the strategy, essentially we're just using conservation of energy to solve these problems. The way I like to do it is draw a picture always to begin, and then sort out each of your heat fluxes due to the different types of heat transfer you might have, and then draw your simplified energy balance at a point or a surface, and then kind of write out your energy equation like I've shown here, and plug in what you already calculated for the Q dots. Okay. Okay, cool. Let's do one more example. This one is a slightly more exciting, I guess. So we are going to consider the energy balance for a thin silicone wafer, shown below. So our wafer is this thing on a little pedestal right here. There's our wafer. And we want to find the time rate of change of the temperature of the wafer, given the wafer's starting temperature is 300 Kelvin. And we also want to find the steady state temperature of the wafer, so TW as time goes to infinity. All right. Okay, so we have kind of an interesting setup here. So we have this wafer that's held up on two little pins, so we can assume that there's convection happening on the top and the bottom of this thing. And we have a chamber that's heating it on the top side of the wafer, and then the idea is that it's cooling it on the bottom side of the wafer, okay? So we are given this convection coefficient for both the upper and the lower sides. We have an HU and an HL. And then we're also going to assume that we have radiation happening for the top and the bottom surface as well, okay? Oh, there's a few things that are given to us in the problem that are not typed out here. So also given, we have that the heat capacity of our material is 87.5 joules per kilogram Kelvin. Our emissivity is 0.65. And our density of our material is 2,700 kilograms per meter cubed. Okay. All right. Okay, so let's draw kind of a simplified picture of what's going on here. So we have our wafer here. All right, and we're going to assume that we have a thin enough wafer that we're not concerned about conduction inside the wafer itself. So we're going to just concern ourselves with convection and radiation, both on the top and the bottom. So we have 4 Q dots to take into account here. So I'm gonna make this color coded. So I'm gonna call this Q dot convection upper. So that's what this little U is gonna mean. And we're also gonna have Q dot radiation with a superscript U to indicate upper. And then we're also going to have Q dot convection for the lower side and Q dot radiation for the lower side as well. We're also going to have to take into account the storage, Q dot storage. Because we want to find dTW dt, right? So we know we have to take into account storage. Okay. There's a few other items that were given to us as well. So we have that this depth is 0.78 millimeters. And then we are also given that the T gas, T infinity, is equal to 700K. I don't know why that's not written on this diagram for the top and the bottom. Okay, when I make these diagrams, I like to kind of write the pertinent temperatures next to the Q dots so I can keep myself organized. So I'm gonna, for T upper convection, we need a T infinity and we need an H. So we have 700K here, and then our H upper was given to us as, I didn't write it down yet. Okay, it's 8 watts per meter squared Kelvin. For the radiation, we're gonna use, we need our surroundings temperature, That's given to us in this chart. So that's our hot zone. TH is 1500 K. All right. And that's what we need there. For the lower convection, we also have the background temperature of the fluid or the gas moving around in there is 700 K again. And then our convective heat transfer coefficient for the bottom surface is 4 watts per meter squared Kelvin. And then last but not least, for the lower side radiation, we're going to use our T surroundings of the lower side is going to be the temperature of that lower cooling zone, which is 330 K. Okay. Okay, so let's do our analysis over, I need another color. Okay, so this is going to be our control volume that we're going to do our analysis over. So I'm going to write our energy equation. So we have dE dt of our control volume is going to equal E dot in minus E dot out. All right. And we know the left-hand side is Q dot storage. And the right-hand side is we're going to group all of the things coming in versus minus the things going out. The way we've drawn this, we have nothing coming in, right? No arrows are pointing in, everything's going out. So I have minus Q dot convection of our upper plus Q dot radiation of the upper plus Q dot convection lower plus Q dot radiation lower. So far, so good. All right. Now I'm going to substitute in all of the expressions that we have for these different types of Q dots. So Q dot storage is C over A dTW dt. And then we have minus the quantity of all of these 4 Q dots summed together. So Q dot U convection is HU times TW minus T infinity upper, and I should give this a U, plus our radiation on the upper is purple, so we have epsilon sigma T wafer to the 4th minus T of the surroundings on the upper side to the 4th. Plus our lower side convection, we have HL times TW minus T infinity L. Plus our bottom side radiation. So we have epsilon sigma TW to the 4th minus T of the surroundings on the lower side to the 4th. Okay. Okay, I want to do a little bit of work on this capacitance here. Because it's not quite, this equation is not quite in a form that we can use. So if you recall, C is equal to CP times M. We aren't given the mass, but we are given density. So let's use volume to work that out. So we have CP, and then mass is just density times volume, right? We were given the thickness of this material D. So we know that the volume is the surface area times D. All right, so I'm going to substitute this in here. So when I have C over A this is CP rho A times D divided by A. And our A's cancel, which is good because I didn't give that to us, right? So that means that this just becomes CP rho times D is all of this. Okay. Okay. So we have all of the values given to us already. And the first thing we want to find is dTW dt at TW equals 300K. Right? So that was the first question. Find dTW dt given the wafer's starting temperature is 300K. So we're going to do that now. So we want to find this. All right, so I'm going to move my CP rho D over to the right-hand side, and then I'm going to just solve this. I'm going to plug in all the values that we have and whatnot. So this is minus 1 over CP rho D times all of this. I guess I'll write it again. All right, so we have this expression. Oops. All right, and we have all of these values as well. So the temperature of the surroundings on the lower side, this is 330 Kelvin. T infinity of the lower surface is 700 Kelvin. HL is 4. On the upper side, 1500 is our surrounding temperature. Oops. This is 1500 Kelvin. And then 700 again for the upper surface T infinity. And then we also have HU is 8. All right, we're using TW is 300, right? So all of these places, we're going to use 300. All right, our emissivity was given to us as 0.65. And then we're also given sigma somewhere. Sigma's given to you, but I didn't write it down. So that one's known as well. And then we know that CP is 87.5. Rho is 2,700. And diameter is something small, 0.78 millimeters. All right, so when we calculate this, we get that dTW dt at TW equals 300 is 104 Kelvin per second. Okay. Okay, we also wanted to find the steady state temperature of the wafer. Does anybody have any ideas on how we might do that? So what happens when something's steady state? What simplification can we make? Yeah, so our DDT term goes to 0. So essentially what we're going to do is we are going to start with this equation. So I'm going to call this equation star. So we're going to set equation star to 0 and solve for TW. All right, and so when we do that, we get TW is equal to 1251K. All right, and so if we draw kind of what's going on here, we have our temperature of our wafer in Kelvin versus time. It's starting at 300, and we know it ends at 1251. And so essentially what happens here is a curve that looks something like this. Okay. We can also look at what the temperature rate of change does over time, which is just the slope of this curve on the left versus time. And we started off with 104 Kelvin per second. And then that rate is going to decrease until it goes to 0. Okay. Any questions on that one? Feels okay? We feel good about energy balances? Okay, cool. Let's take a quick break and then we're gonna get started on conduction. Okay, so we're gonna talk about conduction in a lot more detail. And we're using the heat diffusion equation, basically to determine temperature distribution inside of a solid body. Did you guys do this in 2500? I'm just curious. No? Maybe? It's distant memory. Who knows at this point? Okay. Okay, so first thing I'm gonna do is we're gonna kind of, it's not a bad derivation, but I'm gonna derive the heat equation for you. Okay, so in our review unit that we just finished, we were looking at system level descriptions of heat transfer. So we were kind of reducing our surface to this massless thing. And we weren't concerning ourselves with what was happening inside of the material that was doing conduction. But now we're going to develop an equation that will allow us to look at the details of what's happening inside of the body. Okay, so basically this is an analogy of when we did the fluid mechanics sections going from our integral equations to the differential form of the equations. We're gonna do that exact same thing for conduction. So what we're gonna do is we're gonna say, okay, we have conservation of energy for a system that is only subject to conduction. So we don't have convection, we don't have radiation, we only have conduction. And because of this, what we have is that our dE dt or E dot of storage is equal to Q dot, so conduction in, minus conduction out. So if I draw a differential element, so just a cube here, like so. All right, and I'm gonna give us a coordinate system to work with here. So let's call this X, this is Y, and then this is Z. All right, and so we have our little differential cube that have sides of length delta X, delta Y, and delta Z. All right, and then we have our flow in. So we have Q dot Z. Then this is Q dot at Z plus delta Z. All right, so this is our Q dot in the Z direction. We can do Q dot in the X direction. So we have q dot x, and then q dot x plus delta x. And then last but not least, we have our y direction heat flux. So we have q dot y, and then out the back, we have q dot y plus delta y. All right, so if you look at our box, all of the q dots coming into the box or pointing toward the box are going to be our q dot ins. And then all the ones leaving are our q dots out. All right, so we end up with our qx is coming in and qx plus delta x is leaving. Oh wait, wrong color. So q dot x is coming in, q dot x plus delta x is leaving, q dot y is coming in, and then q dot y plus delta y is leaving. And then same thing for the z direction, we have q dot z coming in and q dot z plus delta z is leaving. Okay. Not too bad. So that is fine. We also know that the time rate of change of energy stored in the system is m times Cp delta T or dt dt. So our change in temperature versus time. And I can expand this out using the idea that mass is just equal to density times volume, where this is the volume of our little cube. Okay. If you recall from the very beginning of our review of heat transfer, heat flux is very often normalized over the surface area. So if we want to switch to our little q, lowercase q dot, we're going to divide through by surface area. So for example, our q dot x, to make that a lowercase q, we're going to divide by the surface area, which is delta x delta z. No, this is delta y delta z. Oops. Okay, so if we take our equation, so we have rho delta x, delta y, delta z, Cp, partial t is equal to q dot x plus q dot y plus q dot z minus q dot x plus delta x plus q dot y plus delta y plus q dot z plus delta z. If we, if we divide through by the volume, so delta x, delta y, delta z, what happens is we get rid of this, and then all of these become lowercase q's. Divided by the leftover length. All right, so in the x direction, we end up with divided by delta x. This is divided by delta y. This is divided by delta z, divided by delta x, divided by delta y, and then divided by delta z. Okay? Which I have typed right here. All right, so I'm just combining the x direction q dots, the y's, and the z's. Do these three terms on the right-hand side perhaps remind you of anything? So if we take the limit that delta x, delta y, and delta z go to 0, we end up with derivatives on the right-hand side. So we have rho Cp partial t is equal to partial q dot x with respect to x, partial q dot y with respect to y, plus partial q dot z with respect to z. All right. Now, I want you to recall Fourier's law of conduction. All right, so we said that all of these Q dots are only because of conduction. So we can still use Fourier's law of conduction and we can substitute them in here. So we've got Q dot X is equal to this. Q dot Y is equal to this one. And Q dot Z is equal to this one. All right. And just to remind you, the kind of base equation for Fourier's law of conduction is this one. This is a vector equation. All right, so if you remember, this is Q dot equals minus K times partial T partial X I hat plus partial T partial Y J hat plus partial T partial Z K hat. All right, so we can write this in component form as minus K partial T partial X. So that's our X component minus K partial T partial Y. That's our J component. And then minus K partial T partial Z. That's our K component or the Z direction component. All right. So I can highlight these similarly here. That's where those expressions have come from. Okie dokie. So when I substitute this all in, we get the heat diffusion equation. Oh, you know what? I have made a mistake. Does anybody see the mistake I made? With the derivatives, perhaps? So I apologize for that. If you go back up to this, the definition of a derivative is the following. So df dx is equal to the limit as delta x goes to 0 of f at x plus delta x minus f at x divided by delta x, right? So all of these derivatives have a minus sign out front. My apologies. All right, so we have a minus sign out front, and then we're substituting in these expressions for q dot x, which has a minus sign as well, so we end up with a positive sign in the end, okay? All right, so when we substitute them in, we get the heat diffusion equation, which looks like this. Generally, and this is almost always the case, as far as I have ever seen, we always assume that K is a constant, which means that this KX, KY, KZ, they're all K. All right. Okay, so if all of these KX, KY, KZ are a constant and they're all equal to just K, we can pull them out of the derivatives, right? And so what's common to do is to lump together all the material properties that appear in this equation. So density, heat capacity, which is Cp, and then K, those are all material properties. So it's pretty common to put them all together. So we divide through by K and we get rho Cp over K on the left-hand side. So I'm just gonna write that algebra down right now. So we have rho Cp over K, partial T is equal to the second derivative with respect to X of T plus the second derivative with respect to Y of T plus the second derivative with respect to Z of T. All right. And this on the right-hand side, this is just the Laplacian of T. This shows up in the Navier-Stokes equations too. And because everything has come full circle at this point, this Laplacian, that's diffusion. All right, so the term that shows up with the second derivatives in Navier-Stokes, that's often referred to as viscous diffusion. So this is thermal diffusion, that was viscous diffusion, okay? Okay, so this is just heat diffusing away inside of a material. In Navier-Stokes equations, that term was momentum diffusing away in the fluid material, okay? Okay. Like I said, it's common to lump these material properties together. And so this 1 over alpha is just the same as rho Cp over K. All right, and this alpha is given a name. It's called the thermal diffusivity. And so this is the tendency of our material to diffuse heat. All right, and it's just these lumped parameters. Okay. Along those lines, there is another useful dimensionless number that relates the tendency of a material to diffuse momentum against the tendency of that same material to diffuse heat. All right. And this is the Prandtl number. So this is the viscosity over the thermal diffusivity. So like I mentioned, the viscous diffusion that happens in the momentum equation for when we were talking about fluids, that had viscosity times that second derivative of all the terms. So this term right here, this is about momentum. It's essentially momentum diffusivity. You can think of viscosity as momentum diffusivity. And then in the denominator, of course, we have our thermal diffusivity. All right, so if you think of viscosity as like a momentum diffusivity, a fluid with a high viscosity like honey, for example, it's going to take quite a long time for velocity to kind of diffuse through that type of a fluid compared to, say, water, which has a lower viscosity. And then the same sort of thing happens with thermal diffusivity. So if you have a higher value of alpha, then heat will tend to diffuse very rapidly through that material. Okay, so to look at the trade-off between those two types of behaviors, we have the Prandtl number. Any questions so far? No? Okay, cool. Okay, it could arise that you want to apply this diffusion equation in cylindrical coordinates. This should be Navier-Stokes. Just like how we looked at Navier-Stokes in cylindrical coordinates, you know, in a very hand-wavy way, that's more intermediate fluids. You can look at the derivation if you want in the book or find it online. But the same equation in cylindrical coordinates looks like this. So if I put this in terms of 1 over alpha, partial t, then this is 1 over r, ddr of r dt dr, plus 1 over r squared, d phi squared t, plus partial z squared of t. Okay? And just to remind you, cylindrical coordinates, you have z, r, and then this direction is phi, or sometimes theta, depending. Okay? Okay, so we have this equation, this differential equation now. and it has two derivatives in space. So it's second order with respect to space. That means that we need two boundary conditions. Okay, so the number of boundary conditions that you need is the number of spatial derivatives that exist in the equation. So since it's got two, we need two boundary conditions. And then there's a first order derivative in time. So that means we also need an initial condition. Okay, so we kind of talked about this at the very beginning of this class, like in the beginning of the semester, not today's class. But I'm going to recap kind of the common scenarios that you can see in terms of boundary conditions with respect to temperature. So the first one is a surface with constant temperature. So this is the same as essentially the no slip condition. So it would look something like this, like the temperature at x equals 0 is equal to T naught, where this is some constant. Another situation you could have is a surface that is perfectly insulated. A perfectly insulated surface means that there's no heat flux through it. So that means if this is our body, this is our x direction, we would assume that this is insulated on this side, which means that q dot equals 0 at x equals 0. All right, q dot is convection, right? So we have minus k partial t partial x at x equals 0 is 0. We can divide through both sides by negative k, and we just say that, okay, this means that the x derivative of temperature at x equals 0 is equal to 0. All right, and we would use this boundary condition. This is the analogy to a free surface for fluids where we said shear stress was 0. Same idea. So instead of having, so analogy to fluids would be free surfaces with no shear would mean that mu du dy is equal to 0 at some place. So let's say it's x equals 0 also. And this means that du dy at x equals 0 is 0. All right, so this is the exact same form of a boundary condition. Okay, so if you remember back to when we were doing Navier-Stokes, you had a two derivative equation that you integrated twice and you got your coefficients from it. So kind of halfway through that separation of variables and integration process, you can apply this type of a boundary condition. Okay. Okay. We could also say that there's a surface receiving a known flux. So if this is our surface, here's our x coordinate system. We're saying, okay, there is a q dot s that's applied here. So we would say that q dot at x equals 0 is equal to q dot s. Q dot is just k partial t partial x. And we're saying this is at x equals 0 and it's equal to q dot s. So now we have another condition for the derivative of temperature at x equals 0, but now it's not 0, it's q dot s divided by k, and we pick up that minus sign. Okay. We might also have a surface that's receiving a heat flux, but that heat flux is due to convection. All right, so in that circumstance, we'd have our body. Here's our x coordinate system. And then we'd say, okay, we have some fluid flowing past, and we're given our ambient temperature and a convection coefficient, H. And now our boundary condition is Q dot convection. So we'd set this up in kind of a similar way, but now instead of Q dot S, we know how we can find Q dot convection, right? So we would say Q dot at X equals 0 for the conduction is equal to Q dot convection outside of our body. So we have minus K partial T partial X at the surface, right? That stays the same, but now our right-hand side is H times T infinity minus T at X equals 0. All right, so this is our temperature of the material. At X equals 0. And this is our temperature of the convecting gas. Or fluid, I guess I should say. All right. And then I'm just going to divide through again by negative K, how I did before. So we have partial T partial X at X equals 0 is minus H over K, T infinity minus T at X equals 0. And the same process applies if the surface is subject to radiation. Okay, and we'll see these. I'm going to do some examples that uses these different types of boundary conditions in a little bit. So you'll see it at work. And by a little bit, I mean now. Actually, I have 2 examples and then that's the end of conduction. It's brief. All right, should we see some examples? All right. Okay. All right, so we have this material and we want to find the steady 1D temperature distribution and the steady state rate of heat transfer across this wall. The wall has a thickness L and a thermal conductivity K, and its surfaces are held at fixed temperatures T1 and T2 respectively. All right, so I'm going to draw my coordinate system on here and I'm going to decide which wall is going to be 0. It's arbitrary as long as you're consistent. Okay, and so given this coordinate system, I know that the temperature in my material at X equals 0 is going to be equal to T1. And then my temperature at X equals L is going to be T2. Sound okay? All right, cool. So we're going to write down our governing equation. That's step 1. So that is our heat diffusion equation. We know we want to use a heat diffusion equation, not just because we're in the heat diffusion equation unit, but because we're talking about the temperature profile in a solid wall. All right, so we have no fluid flow going on in here, no discussion of emissivity, so we know we're talking about conduction, okay? All right, and so that equation looks like the following. So we have partial T is equal to K times the second derivative of T with respect to X plus the second derivative of T with respect to Y plus the second derivative of T with respect to Z. And this should not be K, this is alpha. Okay. Okay, so now let's write down our assumptions. All right, I am going to assume that this is steady. If it's steady, then dt is equal to 0, right? And then we also were told that it is 1D. So t is only a function of x. My choice of using x as the variable for the 1D is completely arbitrary. If you want to just say that that was y or z, it doesn't matter, okay? All right, so that means that derivatives with respect to y and derivatives with respect to z are 0. So we can get rid of these two. All right, and so that means that this equation simplifies to 0 is equal to alpha second derivative of temperature with respect to x. I made this a total derivative rather than a partial derivative because it's one-dimensional, right? So we already said there's no dependence on y and z, so that partial becomes a total derivative. Okay. I can also divide through by alpha, and so it actually doesn't matter what alpha is. We just have that the second derivative with respect to x is 0. Okay, so I guess 3 is simplify, which we did. 4 is solve. All right, so I'm going to write my second derivative in 2 steps, just like how I did in topic 4. All right, and so we're going to separate variables and integrate this 2 times, just like how we've done in the past. So I'm going to separate variables and integrate. So I have the differential of dt dx is equal to 0 times dx. And I'm going to integrate this. On my left-hand side, I just get dt dx, right? What do I get on my right-hand side? What's the integral of 0 dx? Yeah, we just pick up a constant. I'm going to call it c1. Then I'm going to separate my variables and integrate again. So I have dt is equal to c1 dx. Right? And so I just get that t is equal to c1x plus c2. And I'm going to apply boundary conditions to find C1 and C2. I've already written them down up here. These are my boundary conditions. So we have that T is equal to T1 at x equals 0. So that means we have T1 is equal to C1 times 0 plus C2. So C2 is equal to T1. And then on the other side of the plate, we have T is equal to T2 at x equals L. So we have T2 is equal to C1 times L plus C2, which we already found is T1. So I'm just going to solve for C1 now, and C1 is the quantity of T2 minus T1 divided by L. So that's our other constant sorted out. And then all I do next is plug those in. And we get that T is equal to T2 minus T1 over L times X plus T1. Feel okay? Not too bad? Fantastic. Okay, we're gonna go and do a second example that is slightly more involved. All right. So now we're gonna look at the same wall as what we had before, but we're gonna have it exposed to circulating fluids on both sides. So we have ambient temperatures T infinity 1 and T infinity 2, and then we have convection coefficients H1 and H2. So this is a little bit trickier, right? So we have those convection heat transfer coefficients on both, or boundary conditions on both the left and the right-hand side. So I'm gonna just sketch out this problem really quick. So we have our wall. I'm gonna keep my coordinate system here, and then we know that this is L. And this is our wall, so I'll shade it in. All right, and then on both sides we have convection. So this is T infinity 1 and then H1. And then we also have convection on the other side. So we have T infinity 2, H2. We're still assuming steady and we're still assuming 1D. So that means our governing equation is the same. All right, so we still have that 0 is equal to d dx, dt dx. All right, once we separate variables and integrate one time, we have d dt dx is equal to 0 times dx. So we integrate this and we end up with dt dx is equal to C1. I'm going to refer to it later, so I'm going to call this equation star. All right, we're going to do this process again. So we have dt is equal to C1 dx. I don't know why I wrote that one so big. That's ugly. C1, there we go. All right, and then we're going to integrate this. So we get t is equal to C1x plus C2. All right. Okay, so now we need to figure out boundary conditions, right? All right. So what we have is that we have convection on both sides. So I'm going to draw these here. So we have Q dot convection 1, and we also have Q dot convection 2. I'm sorry. I'm going to draw this arrow the other way. Oops. No, this one's correct. This one's backwards. All right, so we're going to assume that heat is going from the surface to the surroundings. All right, that's our positive orientation for Q dot. Okay, so let's do left wall first. So we have that Q dot at x equals 0 is going to be equal to Q dot convection 1. And we know that convection is H1 times T infinity 1 minus T at the surface, which is just T at x equals 0. Okay. Q dot at x equals 0, this is just minus K partial T, well, this isn't partial, dt dx at x equals 0. And this is equal to H1 T infinity 1 minus T at x equals 0. All right, so I'm going to move the minus K over to the right-hand side. So I have dt dx at x equals 0 is equal to minus H1 over K T infinity 1 minus T at x equals 0. So far, so good. All righty. So we're going to do that exact same thing on the right-hand wall. All right, so Q dot at x equals L now is equal to Q dot convection 2. And Q dot at x equals L, so in the conduction part of the wall, we have minus K dt dx evaluated at x equals L. And our Q dot convection at 2 is H2 times T infinity 2 minus T at x equals L. Again, I'm going to move the minus K over to the right-hand side. So I have dt dx at x equals L is equal to minus H2 over K T infinity 2 minus Tx at L. Okay, now the algebra commences. Okay. So what I'm going to do is the following. I am going to use, and I'm going to call this equation 2 stars. All right, so I'm going to make use of both of these equations because I need them both. All right, so what I'm going to do is the following. Let's start with the left wall. What I'm going to do is from equation star, we know that dt dx at x equals 0 is equal to C1. Because dt dx is equal to C1 no matter what x you have, right? So we have that. And then from equation 2 stars, we have that t at x equals 0 is C1 times 0 plus C2. So this is just equal to C2, right? So what I'm going to do is I'm going to take this result and I'm going to plug it in here because we need it. And I'm going to take this result and I'm going to plug it in here because we need it. All right. So what I have is on my left-hand side, I have dt dx at x equals 0. So this is just equal to C1. And this is equal to minus H1 over K times T infinity 1 minus T at x equals 0, which is just C2. All right. So I'm going to store this expression away and hold on to it for just a moment. I have an expression for C1, but it depends on C2. All right. So that's mildly irritating. So now we're going to do the same exact process, but with the wall on the right-hand side. Okay. So now consider the right-hand wall. and follow the same process. Okay, so if we look at our equation for the right-hand wall, we are going to need an expression for dt dx evaluated at x equals L, as well as an expression for t at x equals L. Okay, so let's do, we're going to use equation star again. And we want to find dt dx at x equals L. And if you remember, equation star just tells us that dt dx is equal to C1 all the time, no matter what x location you're at. So we get C1 again. All right. So that is our red box. All right, so that's sorted. And then we also need to use equations 2 star again. So we want to find t at x equals L. So equation 2 star is that C1 times x plus C2 is t. So we have C1 times x is equal to L plus C2. All right, and that is the light blue box stuff. All right, so we're going to plug this in. So we get the following. So we get C1 is equal to minus H2 over K times T infinity 2 minus C1L plus C2. All right, so we have 2 equations and 2 unknowns. I'm running out of colors. Let's do that one. Okay, so now we have this. So we have, and I'm gonna call this one equation 1, and this one is equation 2. So we have equations 1 and equation 2 give us 2 equations with 2 unknowns. So we need to solve these 2 to find C1 and C2. Okay? All right. So there's many ways that we could do this. I am going to solve equation 2 for C1. All right, and so to do this, I'm going to have C1 times the quantity of, well, let's see, C1, and then I'm going to add, I guess I have to subtract because it's a positive number. So I have H2 over K times LC1 is equal to minus H2 over K, T infinity 2 minus C2. Okay. So I'm going to factor out the C1. So I have 1 minus H2L over K is equal to minus H2 over K, T infinity 2 minus C2. And then I'm going to solve this thing for C1. So I have minus H2 over K, T infinity 2 minus C2 divided by 1 minus H2L over K. And then I'm going to set this one equal to equation 2, because they both are C1 equals. Okay, so C1, or equation 1, sorry, was C1 is H1 over minus H1 over K times, wait, T infinity 1 minus C2. All right, so this is equation 1. And this is going to be equal to minus H2 over K, T infinity 2 minus C2, divided by 1 minus H2L over K. I can multiply both sides by K and get rid of it on the numerator. Okay. And now I'm going to try to group my C2s together. So I have H1 C2 minus H2 C2 divided by 1 minus H2L over K is equal to minus H2 T infinity 2 divided by 1 minus H2L over K, and then plus H1 T infinity 1. All right, I'm going to factor out the C2 here. So I have H1 minus H2 divided by 1 over H2L over K is equal to H1 T infinity 1 minus H2 T infinity 2 over 1 minus H2L over K. All right, now I'm just going to divide it through this factor on the left-hand side. So I have H1 T infinity 1 minus H2 T infinity 2 divided by 1 minus H2L over K. All of that divided by H1 minus H2 divided by 1 minus H2L over K. All right, so we have an expression for C2. It's not pleasant, but we have it. And then what we can do is just plug in that expression for C2 back into our equation for C1. So I'm going to call this equation 3. So if we plug this result into equation 3, we find C1. Okay, and then we take these results and we put them, plug C1 and C2 back into T equals C1x plus C2. And then that's it. I think the toughest part of this problem is essentially doing this step. So recognizing that you need to use equations star and 2 star to get the pieces of our boundary condition to plug them into where they go. Beyond that, it should just be algebra. Okay. And this is, I believe, the trickiest version of a conduction problem you could see. But it's mostly just irritating, I think, right? For reference, I won't give you a double convection boundary condition problem for the exam because this is too much algebra. I don't want to test your algebra abilities. I mean, you should be able to do it, but I'm not going to assess that, okay? Any questions on the process? No? In that case, we can end a little early today if everybody's okay with it. I know some of you have an exam after this, so happy testing. Good luck. And I will see you guys on Wednesday. Oh, I did want to mention, and I'll put it on Moodle as well. I think, Wednesday, like this Wednesday before class, during our lab time, I will show you how to use the wind tunnel. Okay, so that should also be helpful for the proposal too. If you have other questions about that, you can ask me then. Okay. All right, cool. I will see you guys in a couple days.